Okay, so we're just covering a little bit of binomials, just what I just wanted to get done. Okay, why is it not working? Okay, anyway, so we're still, what the hell? Okay, yeah, so we were covering what I planned to cover was just a little bit about binomials, just kind of like a revision, yeah. So what first off, I just want to see what binomials are, like how I'll just start working towards what the binomial theorem is, and then we'll start figuring out stuff. Yeah, don't worry. Yeah, okay. What the hell is this? One sec. Yeah. Bye bye. Okay, that's better. No. Wait. Okay. Yeah. Cool. Okay. Sorry, I did not see that coming. Okay. So say if I have like a binomial, right? And so what a binomial is just a pair of terms, right? If I just have a plus b, right? Actually, I'll just use a different pencil because this looks yucky. Come on. Okay. So if I get like a pair of terms, right? Like a plus b, right? This is what you call a binomial. Bi means two. Nomial terms, I think. Nomial would probably refer to terms. So binomial means two terms, yeah? So if I take a binomial to different powers, we start getting something rather interesting. If I take a plus b to the power of 0, right? Anything to the power of 0 is 1. If I get a plus b to the power of 1, anything to the power of 1 is just the same thing as itself. So I just get 1a plus 1b. 1. Yeah? Oh, cool. Okay, if I take a plus b all squared, right, then we start getting something rather interesting. Kind of. I don't know. You probably know this already. This is just in quadratics we apply. So basically we get, actually I'll do this, a plus b times a plus b, right? It's the same thing as, okay, so then a times a is a squared, b times b is b squared, so I'll just write the b squared over here. And then there's a b times a, so that's ab, and then I add that with this a times this b, so that's 2ab, right? So ba is ab, or they're the same thing, and a times b is again ab, so 2ab, just making sure. Okay, a plus b, or cubed, that's just this guy multiplied by another ab, right? So then I just get a squared plus 2ab plus b squared, and I multiply this with another ab, a plus b, sorry. Yeah? So what I end up getting is this a squared multiplied by an a, so I just get me another a cubed, right? Then we're going to get a few a squared b, right? So if I get an a squared b, I can get an a squared b by getting an a squared with a b here, that's 1, 2ab with another a, that's another 2a squared b, right? So that's in total 3a squared b, right? And then we're going to get a term with a b squared, right? So there's a b squared times an a, that's 1ab squared, and then 2ab times a b over here, so that's 2ab squared plus another ab squared, that's 3ab squared, right? That's cool. And then we get a b squared here times b, that's a b cubed. Yeah, all cool? Okay, so just looking at the coefficients, right? So a coefficient is just the term that's, the number that's multiplied by a term, right? So here I'm just going to list it out. If I get a 1 here, I get a 1 here with the first one. The second one, I get 1 and 1. Here, 1a and 1b. Here I get a 1a. I should write 1a. I get a 2ab, and I get a 1b squared. I get a 1, 2, 1. Already you may or may not see a pattern. I'll just continue this. So then there's a 1a cubed, there's a 3a squared b, 3ab squared, and a 1b cubed, right? That's 1, 3, 3, 1, right? So you can see a kind of pattern here. If I add two terms, the one between them, like below and between, is like the sum of those two. And all the way diagonal across is still always 1. So then 1 plus 3 would get me 4. 3 plus 3 will get me a 6. 1 plus 3 gets me another 4. And I get the 1s on the end. This is how I get the coefficients of the terms. But you notice that there's kind of another pattern going on. Yeah, so that there's an a cubed, a squared, a, and no a. Well, there's no a here because a to the 0 is equal to 1, right? So you can say that a cubed, squared, 1, and then 0. And then here there's 0, b to the power 0, b to the power 1, b to the power 2, and b to the power 3. So you see an increasing and decreasing pattern going along, right? And this is the same thing if I write it back to front, right? Because if I get a plus b cubed, it's the same thing as b plus a cubed, right? Because addition can go both ways. Anyway, so you see that there's a pattern going along here, right? Like this special triangle as I drew. This is what I call Pascal's triangle. Well, that's a guy called Pascal invented this or whatever. We just call it Pascal's triangle because we can, yeah. And so this is like basically the pattern in the powers of binomials, but it doesn't stop there. That's the cool thing, yeah. So well, what's cool about this all, right, is that we can apply a special function or a rule to get each and every one of these, right? And how it works is we start applying something from permutations and combinations, right? If I look at this squared thingy, right, with an a plus b with an a plus b, right? Now, if I want to figure out how many ways is there to get an a squared, so to pick two a's out of this, right? Say like if I have a box, right? Yeah, and if I have two objects, right? If I take one out and then I put it back in, and then I take another out, right? So imagine if this is red, this guy's red, and this guy's blue, right? How many ways is, and if I take one out, put it back, and then take one out again, how many ways can I get two reds at a time? So then we start applying this thing called choose notation, right? Or like the choose function or the C, yeah, whatever we call it, right? So basically, like a simplified way of writing this is you would write, okay, so the number of possible ways, the number of possible outcomes is 4, right? We out of the 2, right? How does this work? Yeah, screw it. There's 4, right? 4. Out of the 4, we can choose 2, right? Because there's 2 in the start, and then there's another 2 options in the second picking, right? I think I'm trying to get this myself too. Don't worry. Yeah. So then you write this as a C over here, right? To say that you have 4 options and you're picking 2. Yeah, and you're picking 2 in and there's no order to it. Okay. Anyway, still. If I have me an a plus b and an a plus b, like, you know, how many ways is there to pick an a squared? There's only 1. And the way you write this as is for C0. No, not 4C0, sorry. Because it's between 2 of them, right? That's not 4C2, my bad. This is 2C0, is it? I don't know. Anyway, who cares about that? Forget that example. Anyway, if I'm looking at this, right? Out of the what was I going to say? Yeah, out of the 2 options, kind of. So if I have 2 thingos, how else would I represent this? Yeah, okay. So if I had 2, how would I say? Okay. Actually, this is a really weird way to represent this. I'm so sorry. But anyway, still, the special thing about this triangle thing, right, is that each of the number of terms follow a specific pattern. Because if I write this in terms of this C thingo, right, and then if I start applying the position, right, imagine if I call this the 0th row, because the power is 0, yeah, the first row, second, third, etc., fourth, and so on, right? And if I put this 0 up on the top here, and then if I start applying this guy, right, what I end up getting is I get my top term, right? I'm going to rewrite this in terms of the C thingo, yeah? I get 0C0 on my first top thingy. Then I get 1C0, and then I see 1C1. And then between these two, that's number 2, right? Number 2? Anyway, still. So this is 2C0, then there's 2C1, and then there's 2C2, right? Again, we get 3C0, 3C1, 3C2, and 3C3. Notice how all the edges would be 1, end up being 1 somehow. I don't know, just type it up in the calculator and you see it. And you see how in the middle we would end up getting like interesting numbers and stuff, right? And so each of these follow a certain pattern, right? Imagine if I have the nth row. And in the nth row, I want to pick from the left the kth term, right? So this is the first term, second term, third term. And so in my nth row, like so on, I don't care what number it is, right? I want to pick the kth term from the left, right? Then if I have to represent that, right? Because I start from 0, then I go to 1, then because I'm starting from 0 here, right? Then I have to, then the way to represent that number, I would get n c k minus 1, right? And because I start counting from 0, then my first term would be like nc0, and then it would be nc1, and so on. So if it's my kth term, then it would have to be k minus 1, one less than that, yeah? All cool? What was I going to go with this? I was going to go with this somehow. Oh yeah, so this goes along with our binomial thingo, right? Say if I start counting from 0, right? Actually, how was I going to go from this? I was going to go from this somehow. Sorry, my mind simply blanked. Give me a second to actually like let it reboot. I'm so sorry. Okay. What was I going to go from? How does choose notation relates to this? Okay, so how choose notation relates to this is basically using this choose or the C thingo, we can start predicting the coefficients of the terms that we want to expand, right? If I want to get like 2 plus 5x, right? And if I want to use, and if I take this to power like 6, right? Expanding this all out would be like a massive pain in the butt, right? Easier if I want to find the term, right? The specific term that had the term that had x squared in it, right? If I want to figure out in this whole expansion, what's the coefficient of the term that has x squared in it, right? Then I can start applying this choose thingo to start solving for that, yeah? So how this would work, right, is you see how I got all of this, right? I'm going to represent it by this letter C thing as well, right? If I get a plus b to the power 0, right? This is 0c0, right? And this is just x to the, not a to the 0, b to the 0, because literally nothing's added, right? And it's all equal to 1, yeah? A plus b to the power 1. That's just 1c0, a plus 1c1, b, right? Because I start from the 0, from the left, and then get to 1c1 to the right. Notice how it's pretty symmetrical in that sense, how there's a weird symmetry between like the 1, 1, the 3, 3, 4, 6, 4, yeah? The thing is, the special thing about the C thingy, right, is if I take 3c1 and 3c2, they both are equal to one another. Somehow, I don't know. I don't understand the C thing myself, really, but like you just apply this, know the pattern, know what's going on, just get good in those exams, right? A plus b squared, right? Then I start off with a 2. You see how the highest power and the thing on the top is the same thing. 2c, and this shows the row that we're talking about, and then this shows like the term starting counting from 0, because some people are really weird and they like counting from 0 because they can. 2c0 a squared plus 2c1 ab plus 2c2 b squared, right? Yeah, 2c2 and 2c0 are the same thing, so it can go back to front as well. A plus b cubed, it's just the same thing as 3c0 a cubed plus 3c1 a squared b plus 3c2 b squared a plus 3c3 b cubed, right? And you may or may not see a pattern here, right? The way that we can represent this is first off using summation notion, right? Because we're basically summing a bunch of stuff together, right? So then we can start applying that thing that we learned from series and sequences. I don't know if you covered that or not, but still. Okay, so we got this massive E looking thing. Yeah, we got this guy, right? And this guy means that like we're just adding stuff together, yeah? All cool. And I start from a specific term and end up at an end, right? It has a start and it has an end. Yeah, so let's see. We end with number 3, right? So this number 3 is always the same as the number on the top, right? Imagine if I said if I let this number be n, right? If I let that top number be n, so my finishing number is n, right? And if I have n, c, k, right? And I let k equal to 0. So I start off with 0, right? This 0 guy here, right? And then I add 1 each time until I get to the top, the same guy as this guy, right? But then now we have to relate this all and tie this up with our a's and our b's, right? So how we would do that would be, how would we do that? Oh yeah, so we would just, so we'd have a to the, okay, so this starts with n, right? And it gets smaller and smaller each time, right? So when k is equal to 0, then it would be a to the n. Okay, let's just say n minus k, right? Because as k increases by 1, the power of a decreases by 1, right? So each time k increases, a would start off with the biggest number and then it starts getting smaller to 0, as you see here, times b to the k. You see how this bk n minus k? So because you see, starting from k equals 0, the power of k here it starts off as 0. How it's all multiplied by 1, and then the power when k equals 1, right? So you add when k equals 0, when k equals 1, when k equals 2, and so on, until it reaches the maximum term, right? And this is a generalized term, right, for some power n, right? So if I take a plus b to some power n, this is actually what you call the binomial theorem. I literally just jumped a few steps because I literally just went like to the last stop point. Anyway, still, this is basically what your binomial theorem states, right? Because I can do n minus k, b to the k, right? But then again, what I can also do, right, is I can flip all of this back to front. So the last term is now the first term because it's all addition, right? So when you add things, the order doesn't really matter, yeah? So I can also write this as a big E looking thing. It's actually sigma, but still, k is equal to 0, and I end up at n, right? I always do that, n ck. But instead of the powers of a n minus k, I can do a to the k, and then b to the n minus k, right? Because I could start from 0 here, a to the 0, plus a to the 1, plus a to the 2, plus a to the 3. So I can go backwards as well. And these both are literally just saying the same thing. Oh, cool. Where was I going to go from this? I had something, and then I just forgot what the hell to do. Okay. Finding coefficients of specific terms in binomial expansions, right? Let's just, I think the easiest way to go for this is just to tackle a specific question. And you may understand the method of how to work it, yeah? Okay, say if I do 1 plus x, right? 1 plus x, right? And I'll take the power 8, because I can, right? Now, what's the coefficient? So what's the number that's multiplied? So I'm trying to find the coefficient of x to the, I don't know, 5th, because I can, right? The coefficient of x to the 5th, right? How I would do this, instead of expanding the whole thing out, because that's a pain, right? We can apply this special E looking thing, yeah? Sigma. So then I start from k equals 0 to 8 this time, because my highest power is 8, right? And then we do 8 ck of 1 to the k times x to the n minus k, right? So then 1 to any power is equal to what? 1, right? So this guy doesn't really matter, right? Yeah, all cool? Right? I can write x to the k or n minus k because 1 to whatever power, it doesn't really matter. Yeah. So then we want to find the term of x to the fifth, right? That means n is 8, or we already know that, right? So then we have to find the coefficient when we find x to the fifth, right? So that means 8 minus k would have to be equal to 5, right? So that means k would have to be 3. So when we sub k equals 3, then we get our coefficient, right? We get that guy. So then basically the coefficient would be 8c5. And you literally just type it up in your calculator, 8c5, and then it will spit you out some number. And I really don't care what that number is because you can literally just type that up in the calculator. Yeah, all cool? So you see how the method would go. I'll just do like another question, right? If I just pick 2 plus... Okay, yeah, this is a more interesting one, right? If I look at this guy, x squared plus 1 over x all to the power 9, right? So now I want to figure out, say if I do the coefficient of x, is there an x cubed? There's going to be, yeah, I shouldn't actually make up questions, lol. Making questions would be really, really weird. Okay, yeah, no, that's dodgy. This looks like a legitimate okay-ish question. No, I don't like fractions. Fractions are yucky. I just want you to get the method, right? So then if I do 2 plus x, right? Yeah, go away. Okay, 2 plus x. And if I'm taking that to the power of 7, right? Just got a copy from the textbook. Pick one, x squared or x fourth, just do x fourth, right? So the coefficient of x to the fourth, right? So now we're just trying to figure that out, right? Because it's like, this may be a common question that we may be assessed on in an exam. I think. Maybe. It's okay. I just want to help out. Anyway, so when I'm looking at this guy, right? We can apply our special sigma thing here, right? Now the sum of all this, right, is like taking the whole expansion. If I want to take a specific term, then I just get all this part, right? So I get, instead of 8, sorry, I get 7, right? 7c, some value k, right? All the x to the k, and then times 2 to the n minus k, right? It doesn't matter if x is to the n minus k or 2 is, because they both increase or decrease by the same amount, right? That don't really matter, right? So the coefficient of x to the fourth, right? So that means in this case, k has to be 4 to actually get a value, right? So then when I sub k equals 4, then I get 7c4 times 2 to the, okay, this is actually 7, n is 7, right? So then times 2 to the 7 minus 4 is 3. So 2 to the 8. Anyway, x to the 3, right? So this is my whole coefficient, right? This is the whole set of numbers multiplied to x cubed, right? All cool? Okay, if I do something really odd like x plus 1 over x, right? Now these both are like related to each other, kind of, you know? And if I take this to the power like 7th, right? Imagine if I want to figure out, like, I don't know, the x squared term, if there is one. I don't know if there is. Okay, then I take 7ck, right? And then I get x to the k, and then I get 1 over x, all to the 7 minus k, right? Oh, cool. Yeah. Now what? Oh yeah. Wait, let's just like play around with these numbers a little bit because we can, right? Zk, right? And then what I can do with this guy is I can do x to the k, right, all over. Now the 1 to the 7 minus k, that's going to stay the same. This is just going to be x to the 7 minus k. Do you see how this works, right? Because 1 over x to the 7 minus k, right, is equal to 1 over 7 minus k all over x to the 7 minus k, right? And so 1 to whatever power doesn't really matter. It's just the x that really matters more. Yeah. If I multiply both sides by x to the k, right, then I get 7ck x to the 2k, right, because it's 7 minus k, right? If I multiply both sides by x to the k, x to the k, yeah, both this minus k and this plus k cancel out. This is basically what I did. So this x to the k times x to the k just gets x to the 2k all over x to the 7, right? So I can represent this whole thing as x to the 2k minus 7, right? Because it's over 7. Yeah? Oh, cool. I think this should be fine. Where was I going to go from here? I'm so lost. Okay. Okay, fine. Let's find the coefficient of x to the... Can we get something like... Okay, let's find the constant term here, right? So the constant term is... No, wait, not the constant term. We're not going to get a constant term, are we? I don't think so. No, I don't think so. We will. No, wait. I'm just trying to make up a question here. And making up questions is pretty hard on the spot. Let's see. Okay, yeah, sure. Let's do x to the cube, x cubed, right? Let's find the coefficient of x cubed, right? If I let x to the 2k minus 7 is equal to x cubed, right? And then we know that 2k minus 7 is equal to 3. 2k equal 5, not 5, sorry, 10. Skipped ahead. K is equal to 5, yeah? So then I sub k equals 5, 7, k, sorry, my brain's broken. 7c5 times x to the cubed, right? That's basically it, right? So then we basically end up with our coefficient, which we can just plug it into a calculator, and we just end up getting our result. Yeah, all cool? Now, that's how you find the coefficient of specific terms in binomial expansions. Finding the greatest coefficients are a little bit harder, but it's not that yucky. I think not. Watch this, yeah, all cool? Let's just look at a question like maybe, wait. Yeah, we need to start applying things like this guy, right? You see the 1 plus x to the 16, x to the 13, x to 11, yeah? So we start applying things like these guys, right? Let's just do that. 1 plus x to the power 16, right? I want to find the ratio of the term, so x to the 13 all over x to the 11, right? And I want to find the ratio of the coefficients, right? So then I get like something, yeah? Oh, cool. Okay. So the term with the x to the 13, right? The ratio of the term in x to the 13 to the term in x 11, right? So the term in the x to the 13 would be, well, this would still be 16 c k, I don't know, times x to the k, right? Because one times, I can as well write 1 times n minus k, right? Well, 1 to whatever power doesn't really matter. Yeah, all cool. So then x to the 13, we'll just get 16 c 13, all cool. And then yeah, forget that. Anyway, yeah, so 16, I get 16 c 13, right? And then for this guy, in a similar fashion, then I get 16 c 11, right? And so the ratio of the term of the coefficients, right, would be these guys. Yeah, and you just plug it in your calculator and you just got your answer, right? So then when we start applying things like this, then we can start getting the largest term, right? And how we get the largest term is, okay, in this way, right? Then if I expand it out, then I will get, okay, just visualize this kind of, okay, 16 c0 x to the 16 plus 16 c1 x to the 15 plus 16 c0 2, sorry, x to the 14 plus 16 16 c3 x to the 13 and so on, right? Now, if I take the ratio of this term over this term, right? If I get 16c1 all over 16c, what's that, 0, right? Now, if this ratio is greater than 1, right? Yeah, if it's greater than 1, that means this term is bigger than this term, right? If I have like some number a over b, and that ratio is greater than 1, that means a is definitely greater than b. Yeah, so this term is definitely greater than this term. Oh, cool. So then we basically just start dividing out the terms. So then when is 16ck all over 16, but then the moment where it starts getting less, right, that shows that's where it's the biggest, that's where it shows that it starts getting smaller, right? If I start looking at here, right, then if I start looking at the ratio, right, then 4 over 1 would be 4, so that's still bigger. 6 over 4 would be 1.5, that's still bigger. But then when I do 4 over 6, it's what, 2/3, right? And that's less than 1. So that means this term would be the biggest term. You see how I would, the biggest coefficient, sorry. So this is how I would solve for the biggest coefficient. So as soon as it starts getting less than 1, then the denominator would be the biggest coefficient. You see how it always starts increasing and then it goes down. Yeah. So then we start applying this idea. 16ck, right? All over 16ck k minus 1, k plus 1, k. Okay, I can do k. Wait. The top one is our top term, and that means this is k minus 1 because of the term behind it, right? Oh, cool. From here, right, what we can do is we can apply the formula for c, because I haven't actually told you this yet. I'm just gonna like shove it in your face because I can. I'm sorry. Okay. If I take a, c, b, right? Actually, if I take n, c, r, that's how they say it sometimes. I don't know why they pick n and r, but they just do. It's just n factorial. Factorial is, I'm pretty sure what you know. If I take 5 factorial, it's equal to 5 times 4 times 3 times 2 times 1. Only finishing off at 1. Yeah, all cool. If I take n factorial over r factorial, n minus r factorial, right? If I start applying this, right, then I can start getting me something interesting, I think. 16 factorial all over k factorial, 16 minus k factorial, right, divided by 16 factorial all over, now this is k minus 1 factorial, and then there's 16 minus k minus 1, minus k minus 1, okay, factorial, yeah, oh cool. Now, you see how clearly the 16 factorials cancel out. We end up getting is this guy's going to be flipped up, right? This guy goes up, and then this guy ends up, because this guy goes on the bottom, they divide out. So this guy is cancelled out. We end up with a k minus 1 factorial. So this guy on the top of the fraction. Okay, 16 minus k minus 1, right? The minus 1's become a plus 1. So then we get a 17 minus k factorial. Oh, cool. And I get a k factorial. And then we get a 16 minus k factorial. Okay, now we just start applying something very interesting from factorials, right? What we can apply is, if I have 6 factorial, right? Yeah, this is just the same thing as 5 factorial times 6, right? Because it's 6 times 5 times 4. So it's the same thing as the one before it. It's just, so then if I have n plus 1 all over, n plus 1 factorial all over n factorial, right? That's the same thing as just n plus 1, right? Because n plus 1 factorial is n factorial plus, multiplied by the n plus 1. I hope I'm not confusing you anywhere here. If you have any doubts, just let me know, okay? And I'll go through this a little bit more slowly and properly with you, yeah? I know it seems like a bit of a rush because I probably am taking a lot of time here. I'm so sorry. If you have the time, please go through this. It means a lot. Thanks. Okay. So if I take k minus 1 factorial over k factorial, right? It's like the reciprocal this guy, right? It's opposite of. So then I get 1 over k, looking at these two only, right? Now 17 minus k factorial and 16 minus k factorial. This guy is 1 bigger than this guy, right? Because this guy is 1 bigger than this guy, that means then we'll end up with a 17 minus k, and this guy cancels out completely, right? And when I multiply this through, then I just get 17 minus k all over k, right? Now what do I do? Oh yeah. So then this ratio is the same thing as this ratio, right? And so as soon as this starts becoming, so then 17 minus k all over k has to start becoming less than 1, right? Now when it starts becoming less than 1, k is always a positive number, right? Whenever we're dealing with this, if it's a negative number, then we have to start flipping the sign and all that. We know that k is always a positive number. 17 minus k is less than k, right? Add k on both sides. 17 is less than 2k, right? So 17 over 2 is less than k. Yeah, all cool? So now if 17 over 2 is less than k, right? Then wait, this is it the smallest thing? The smallest whole number of k that would satisfy the solution would be, let's see, wait, 17 on 2 is like what, 8.5, right? So the smallest value of k that will follow this rule is 9. And you can test it out over here, right? 16c9 all over 16c8, right? I'm just going to plug this into the calculator, right? Plugging this in the calculator, 16c9 all over 16c9 all over 16c8. This gets me 8/9, right? If I apply the same thing for, yeah, as a 16c9 over 16c8 is 8/9, right? So it does follow the idea that yeah. So 16c9 over 16c8 is a number less than 1. You see that, right? So we already know that when k equals 9, that is our biggest coefficient. Sorry, when k is equal to 8, remember the bottom term is the bigger one, right? So when k is equal to 8, we get our biggest coefficient. Yeah, that's cool. Yeah, is there anything else that should be done? If there's any, these are like the main types of questions that you may be assessed on. If there's anything new that pops up, I'll go through it with you. Yeah, all cool. Yeah, thanks a lot for your time. See you soon. Have a great time. Good luck for reading it. Yeah. All right. See ya.